Okay, everybody, welcome to Conceptual Physics today. Woo! Okay. Okay, so we're talking about gravity. Our objectives are as follows. Explain that gravitational force becomes stronger as the masses increase and rapidly becomes weaker as the distance increases. Okay, so that's a good one. Also, evaluate the concept that free fall acceleration near Earth's surface is independent of the mass of the falling object. You've been doing math with that already, so you know that. We're going to evaluate it. And then demonstrate mathematically how free fall acceleration relates to weight. Okay. And describe orbital motion as a combination of two motions, which is something that has a lot to do with what's going on today, if you know about the what Elon Musk and his SpaceX company is doing. Okay, so this is the law of universal gravitation. Remember, we're talking about Newton, and we talk about universal gravitation. So what does that mean to you guys and girls? Okay, so that's good. Yeah, so it's universe. It's the law of gravitation of the whole universe, and you know, it's unimaginably big. It's unimaginably big. And we also said universal means that it's all around. And that is right. It's universal. It's all around. Can't get away from it. There's no place that it's not working. And the law of universal gravitation is something that Newton definitely made really more clear and kind of famous. Okay, so here it is. Sir Isaac Newton, 1642-1727. He generalized his observations on gravity in this law, the law of universal gravitation. Okay, it's a good question. So this is the law of universal gravitation. Now let's see a little bit more about what he said about it. Here's the equation for you. Okay, so I know you guys love equations. Here it is. Big G, which is universal gravitational constant. So universal, gravitational constant. And so this is like a fix-it number, I call it, because this relationship here with the other pieces, the two masses and the square of the distance, I don't like that D. It should be an R. Why don't you put an R there on your notes instead of D? Because D makes you think of diameter, it's actually the radius squared. They have D there because they're saying distance from the two masses. But if I have a big M here, then at a radius, you guys remember we did that line with the radius, right, already? So you remember what radius is? So at a spot that's a radius away from the center of mass, there's going to be this force of gravity. So if I have a little m over here, so there's one m is the planet, and the other m is like a satellite or a moon, which is a satellite. You know, there's going to be a force of gravity in both ways, and it's going to be the same at the same radius. So in reality, it's a sphere. It's a sphere that surrounds the big mass. And at each point, there's going to be a force of gravity depending on the other mass. So that's what it means. Hey, I got one mass and another mass multiplied by each other. Those are so for instance, you guys have mass, right? So each of you have a force of gravity towards someone else and everybody at all times. It's hard to measure when the masses are so small. It's easy to measure the force of gravity on our mass from the Earth, because it's huge. Okay, so I guess there's no questions, but this universal gravitation, like I said, this is the distance between the two masses. It's a radius because it's circular, so change it up just a little bit. Okay, and this just says what we said. M1 and M2 are the masses of the two objects, and D is the distance between the objects, which I want to tell you, put R for radius, because that's really what it is. And that's what it is on all the AP physics sheets. So might as well be ready for that later, right? G is a constant, okay, and so I call it a fix-it number. Big G is that universal constant. Like the relationship is here with these numbers, but they're just offset. So, you know, if you have like, if you have a graph of numbers and you see that that relationship is right, but you go out and you actually make the measurements, and the measurement is showing that, hey, that's not quite right. It's actually like this. Then to move this line over, then you use what's a fix-it number. And that's kind of how I think of these constants, because the relationship is really in these, but then this is kind of a fix-it, so it like really fits what's what we're measuring in the lab. Okay, so if you understood that formula, and you know the M is in the formula, that's mass in kilograms, right? And this says all matter is affected by gravity. And mass is the measure of the amount of matter. The matter is the stuff that everything's made out of. Okay. Two objects, whether large or small, always have a gravitational force between them. So you and the desk, you and your pencil. And in fact, there, you know, used to be a big lab in Europe, and they'd have a big ball here, big massive ball hanging from a string at a right angle. And then when they put another ball in there, what happened is this was no longer a right angle, but these balls actually came a little bit closer to each other. And I'm drawing this, you know, as they're really close, but they're not. But there was a measurable difference in the angle. It wasn't just straight down, which showed that there was a force of gravity that was between and attracting these two balls to each other. Okay, and I wonder if it's still over there, but it was a big. Okay, so I think that's interesting. They used to have that picture in the textbooks. I wonder if it's still around. When something is very large like Earth, force is easy to detect. Right? Like if you fall off a cliff, you know where you're going, down, right? And that's the force of gravity. Gravitational force increases as the mass increases. Okay, and the mass of the Earth is huge, and that's why it's so easy to detect our force of gravity to the Earth, or it's hard to detect our force of gravity to each other. Okay. And then gravitational force decreases as distance increases. So you can say this, it has a inversely proportional relationship, the force of gravity has an inversely proportional relationship to the distance between the two masses. And so when you see this relationship, then when you go to write a formula, if this is on the bottom, then whatever is in relation inversely to the force of gravity is on the bottom. Okay? And then if you look at the force of gravity as it relates to mass, do you understand that if you go to the moon, the mass is less, right? Of the moon, do you weigh more or less on the moon? Less, right? So that means as the mass of the moon goes down, the force of gravity goes down, so that's directly proportional. So that means the mass of the big body would be up on top. And then if you think about, like, for instance, me, the mass of me versus, like, let's say Becca, who's going to have more gravity? Like, who's going to fall harder? Like, for instance, if you got in between Becca and I falling to the earth from the same height, who's going to hurt more? Me, right? Because the force of gravity is forcing on me more, and it's going to turn out to force onto you more if you would be in between. You know what I'm saying? And if you don't believe that, step on a scale. That measures the force of gravity. So that's the other M. So one M is the mass of the Earth. The other M is the mass of whatever you're talking about in this situation. Okay. So this is kind of just going over what I was talking about with those balls. the law of universal gravitation. It says that, hey, these objects are smaller, so the gravitational force is smaller between them. These are bigger, which means the gravitational force is larger between them. So if you had a big one and the small one, the gravitational force there would be in between these two. So if this one was small, this would be medium, this would be large for the force. So they don't have to be the same size. If one or the other is bigger or smaller, it has an effect. If they're both bigger or smaller, it has a double effect. Okay. Now, if you look down here, it says the force of gravity rapidly becomes stronger as the distance decreases. So this right here, this distance from here to here is what we call R. And so if you look at the force of gravity relationship, so that's the R, so it's the distance between the two and the force of gravity. This is the graph. You should write this down. It's called an inverse square law. And both ends would be asymptotic. You know what that means? That means that it never actually touches the line. Okay. So the force of gravity, so when it says right here, it's rapidly becomes stronger, that's talking about going from here. Okay, so if I'm at that radius and then I'm getting closer, because the radius is getting smaller, that means that these objects are getting closer and closer and closer. So from here to here, there's a big change in the force of gravity. That's what the whole rapidly becomes stronger thing. So as we go in this way on the graph, the increase is exponential. If we're increasing our distance, getting further and further away, the decrease is inversely exponential. Okay. Do you have any questions about what I just said? Okay, so free fall and waves. So we've been talking about free fall for a long time, right? That's little g. But, right, just to refresh your memory, free fall is the motion of a body when only the force of gravity is acting on the body. So this is really saying nothing that we see on Earth is ever in free fall, even though we've been talking about it like projectile motion. We've been doing all the math in free fall. What have we not been talking about when we're doing the math with like the soccer putt and stuff? What have we not been calculating? Becca. Yes, exactly. Thank you. Air friction, because that would cause another force to be acting on the body. But free fall would be without air. It would happen in space, but it doesn't ever happen here on Earth unless you evacuate a cylinder or something of air, and then you can do free fall experiments, kind of. Okay. Free fall acceleration near the Earth's surface is constant. What do we call that? What do we use, you guys? Little g. So it's free fall acceleration. You've been using it for a while now. Little g, and we say it's 10 meters per second squared towards the center of the Earth, right? That's how we've been doing our math. It is variable depending on where you're at on the Earth, according to your relationship to the center of mass and the density of the crust where you're at. But we use 10. Okay, if we disregard air resistance, all objects near Earth accelerate at 9.8 meters per second squared. That's kind of the accepted value, 9.81 on average at sea level. But like I said, we use 10 for our calculations, and it does get bigger and smaller. Like if you go up on a mountain, it's smaller. In fact, there was a time when I went to a track meet that was like 7,000 feet above sea level, and the head coach was telling me about his first meet up there. He disqualified people for bringing discuses and javelins that were too light. The implements are too light. So he said, "You're out of here. You're trying to cheat. Well, it became quite a big deal, later at the coaches meeting, and one of the coaches asked the new coach, he said, hey, did you adjust your scales for the elevation that we are above sea level? And that new coach said, I have no idea what you're talking about. And so he had to change his scales, because if you look at our scales right there, they're all according to the accepted G. So the spring goes down according to the accepted G, and it gives out a gram rating. If you go uphill and the accepted G is less, that is going to give you the wrong reading. So he has to adjust the scale, or at least adjust the measurements. And this guy was he ended up being a famous coach, like on the cover of Sports Illustrated and everything, because he had like 20 years of state championship cross country teams, because they got to train so high and increase their oxygen receptors and red blood cells because of that, because the body adapts. Okay, so free fall acceleration is often abbreviated as letter little g. We know that. Okay. Free fall and weight. Weight is equal to mass times free fall acceleration. Here's your formula. Ready, everybody? Write this down. W equals your mass times little g. So remember, your mass is in kilograms. Little g is in meters per second squared, and we use 10, like I said. So that's the weight. Go ahead and use 9.8 for the assignment, though, because I'm thinking that's what the book used, and I took these questions out of the book. Okay, so weight equals mass times free fall acceleration. That's what we're just saying right there. Any questions about that formula? So if you look at the formula that we were talking about yesterday, that was force equals mass times acceleration, right? So weight is mass times acceleration. The force of gravity is a force, same formula. It's just we're calling it weight if we're trying to measure. Like if you step yourself on a scale, you get a weight, and you're actually measuring the force of gravity on your body. So little g is that special case acceleration. Okay, so you're going to have to know that formula. Weight is different from mass because it's the measure of the force of gravity. Mass is a measure of the amount of matter in an object. That's all review. Weight is the gravitational force of the object. Okay, so keep this in mind. One average size apple weighs how much? Do you know? What? 1 Newton. So one average size apple, before they loaded them up with hormones and stuff like that, just like one normal regular average size apple weighs about 1 Newton. 1 Newton is equal to 0.225 pounds. Should be easy to remember, right? Because remember Newton and the apple and all that stuff. So you can actually get a realistic feeling of how much 1 Newton weighs. Okay, so this is just a little bit of an expression of how weight influences shape. And maybe it's better stated that the gravitational force is really what's influencing the shape. It's the gravitational force and the material that whatever you're weighing is made out of. Okay. Velocity is constant when air resistance balances weight. So let's say you're a person falling, right? And so you got a weight of this person is 500 or 600 newtons. Okay. So basically 0.225 pounds, like you take your weight in pounds and you multiply it by more than 4, and that's your weight in newtons. So I don't know why we don't use newtons in America, but maybe it's because the number is just too big and we don't like the way it sounds. I'm not sure. but I think newtons is kind of the general weight that people use throughout the world besides here in America and a couple other countries. Okay, so if you fall, what happens when you fall? You get hit, right, by air. And if there's enough air hitting you, you're going to get a pretty big force, right? And the way to get more air to hit you is what? What do you guys think? How do you get more air to hit you? Okay, so increase the surface area is right, but that can't be the answer for this one because the person's not getting any bigger. But do you agree that if you fall faster, that you're going to be hitting more particles per second? Yeah, so that's what happens. So once you fall so fast that your weight, which is, you know, causing your body to move downward, is exactly counteracted to the force of air, then you quit accelerating. There's a special name for that, and it's called terminal velocity. So terminal velocity is the fastest that something will go. Terminal means end, right? So if you're at like an airport terminal, it means the end of the line. It's like you landed, you're at the end. That's what terminal means. So terminal velocity is the end of the increase in speed. It's the fastest you're going to go. Now, if you watch some of these talented skydivers, if they want to go faster, what do? They change their surface area that is getting hit by the particles because the particles are going that way. So see how many more particles you can hit when you're laid out that way versus in a dive? And so that's where that change of surface area comes into play. Okay, so we're going to be done with this instructional video for now. But the idea is that you guys go and you watch this video here because you're going to need it in the lesson. So it says, in this video, 9.81 meters per second squared is used for acceleration due to gravity. But in our book, and for your math calculations on the quiz and the test, use 9.8. So there I said it. So for this, you have to use 9.8 for little g. I know that we've been using 10 the whole time, but for this lesson, I want to use 9.8. So right here is the website, or I mean, the website that you find this. You can search up this video called, it's called, what is the weight in newtons that an object, or what is the weight in newtons of an object that has a, maybe this is the best little link here for you guys. It's a little bit easier to put into your computers. And I'm just doing this in case the links don't work on the PowerPoint because we had some troubles with it yesterday. So let's stop here. You guys go ahead and watch this video and it'll explain how to do some of this math. Okay, have a great day.